Welcome to my YouTube channel. My name is Venon Insofa, and in today's video we are going to look at insulin hormone. So this video is going to be amazing. It's going to be interesting because we're going to talk about a lot of things in this video. That's why I'm urging you to make sure that you watch the entire video so that you benefit a lot. But if you're new to my YouTube channel or you've been here before but you've not yet subscribed, I'm kindly asking, please go down and subscribe. Hit that subscription button. Make sure that you like, share, and also don't forget to comment in the comment box. I'll really appreciate. Tell me what you think about this video in the comment box. So let us dive into it. So when we talk about insulin hormone, what are we talking about? Many of us are familiar with this hormone, or we've heard about this hormone before many times. So when we talk about insulin hormone, we're simply talking about a peptide hormone that is produced by the beta cells. And this peptide hormone has got 51 amino acids. So insulin hormone, it is produced by the beta cells and it is stored in the vesicles within the beta cells. Now, what we need to ask ourselves is, when is insulin released? Since it is stored in the beta cells, now when is it released? So insulin is released when you have got high level of glucose in the blood. So in other words, we can say it is released during well-fed state. Now, what do we mean well-fed state? So well-fed state will simply mean a state after eating a meal rich in carbohydrates, fats, also we can say proteins. So after eating that meal rich in carbohydrates, what will happen is that the level of glucose in the blood is going to increase. And high level of glucose in the blood is a stimulant for the release of insulin from the beta cells. So we're going to understand how is glucose able to stimulate the release of insulin. But it's not only the glucose that triggers the release of insulin. There are other things. Amino acids, they also cause the release of insulin from the beta cells. What else? We also have what we call incretins. So incretins, these are hormones that stimulates the release of insulin. So we have got two main incretins. Or in other words, we can say we have got two main hormones that stimulate the release of insulin. What are these hormones? So the first one is what we call glucagon like peptide 1 hormone. So glucagon like peptide 1 hormone, this is a hormone that is produced by the L cells. So the L cells, these are cells that are found in the distal ileum as well as the colon. So the L cells, they produce glucagon like peptide 1 hormone in response to glucose and fat acids in the GIT. So the L cells, when they release glucagon and peptide 1 hormone, it goes to the beta cells where it stimulates the release of insulin. We are going to understand how that happens. And what you should know is that we have got drugs that mimics the activity of glucagon like peptide 1. And these drugs are used in type 2 diabetes. We also have another incretin hormone that is called glucose-dependent insulinotropic peptide. It is also known as gastric inhibitory polypeptide. GIP, this hormone, it is produced by cells that we call the K cells. So the K cells are found in the duodenum and duodenum. So the K cells, when they produce this hormone, which is GIP, it goes to the beta cells as well, and it stimulates the release of insulin by the beta cells. So now let us understand how glucose, GLP-1 and GIP are stimulating the beta cells to release insulin. We are going to look at the beta cell. Let us zoom at this beta cell and look what is happening inside this cell. When you look at this beta cell, you can see that this is a blood vessel. So we've got a blood vessel right there, and it is containing, those are glucose molecules as well as red blood cells. And then we've got, this is the beta cell right there. So this beta cell has got these proteins that we can see there. So what are these proteins? So what we have here, this is the GLUT2 transporter. So the GLUT2 transporter, this is the transporter that transports glucose into the beta cell. And what you should know that we've got many types of GLUT transporters. So we've got a lot of GLUT transporters. So we've got GLUT1, GLUT2, GLUT3, GLUT4, all the way up to GLUT14. And what you should know is that these GLUT transporters, they are tissue specific. In other words, each GLUT transporters has got its own specific tissues where it is found. So when we talk about GLUT2 transporters, these transporters, they are only found in the beta cells as well as the liver cells. So we've got the GLUT2 transporter right there. What else do we have? We've got this protein right there, which is called ATP sensitive potassium channel. So this ATP sensitive potassium channel, it transports potassium from inside the cell to the outside of the cell. And it depends on ATP. In other words, it is sensitive to ATP. It is inhibited by ATP. We also have another protein right there, which we are calling L-type, voltage-gated calcium channel. So this channel is activated by voltage. So it can be activated by action potential, and it allows the influx of calcium into the beta cell. So when you've got high level of glucose in the blood during well-fed state, that glucose will go to the beta cell. and it's going to enter the beta cell via the GLUT2 transporter. So we can see the GLUT2 transporter right there. So glucose will enter this beta cell. Now, when glucose enters the beta cell, what is going to happen? So this glucose in the beta cell is going to be converted to ATP. So glucose is going to enter the beta cell, and in the beta cell, it will undergo glycolysis, TCA cycle, and electron transport chain to produce ATP. Now, when this ATP is produced, remember we talked about the ATP-sensitive potassium channel right there, which is found in the beta cell membrane. So this ATP, it's going to inhibit that channel right there, which is ATP-sensitive potassium channel. So it binds to the channel and closes this channel. As a result, potassium cannot leave and go to the outside of the cell. So, in other words, when this channel is inhibited by ATP, it means we're trapping potassium inside the cell. And what you should know that potassium is positively charged. So it's a positively charged particle. So when it accumulates inside the cell, what happens is that we are going to increase the number of positive charges inside the cell. As a result, we can trigger action potential. So action potential is going to be triggered. And when action potential is triggered, you'll find that this action potential is going to activate the L-type voltage-gated calcium channels. So we're going to open these channels. As a result, calcium will be able to enter. So calcium will flow into the cell. So we can see calcium right there. Now, let us go to insulin. So insulin, it's a protein that is produced in the liposomes. So when it is produced in the liposomes, it is produced as pre-proinsulin. So when it comes from the liposomes, we call it as pre-proinsulin. So now, pre-proinsulin will go to the endoplasmic reticulum. So in the endoplasmic reticulum there, the signal peptide is removed, and then it becomes proinsulin. So proinsulin, proinsulin is made in the endoplasmic reticulum. And the proinsulin, what you should know is that it has got three things. It has got A chain, B chain, and the Cpeptide sequence. So what happens is that this proinsulin, it means it is inactive. So can't work as such. So what will happen is that the endoplasmic reticulum, they are going to send proinsulin to the what? To the Golgi apparatus right here. So we have got this green Golgi apparatus right there. So the Golgi apparatus, they are going to convert that proinsulin, which is containing A chain, B chain, as well as the C-peptide sequence. So what will happen that the Golgi apparatus, they are going to cleave that proinsulin into A subunit, beta subunit, as well as C-peptide. So C-peptide is going to be released. And this C-peptide is very important. Now, what happens is that these Golgi apparatus, when they cleave proinsulin into those things, they are going to package everything in one vesicle. So they're going to package C-peptide sequences and A and beta subunits. So A chain and the B chain, these are what makes insulin. So what happens is that the Golgi apparatus, they are going to package the C-peptides together with insulin. So insulin, what you should know is that it is made up of A chain and the B chain, while the C-peptide is not part of insulin. So in the Golgi apparatus are going to form vesicles, and they are going to package C-peptide together with insulin, which consists of A chain and the B chain. So we can see that the Golgi apparatus, they are making those vesicles right there. Now these vesicles are containing insulin, as well as they are containing C-peptide sequences. So C-peptide sequences, they're right there. So when you look at these vesicles, they have got proteins outside there. So those are little proteins on the vesicles. So now, what are these proteins? So these proteins are important. What are they important for? You can see that these proteins, they're also there on the cell membrane. So I've got membranous proteins as well as vesicular proteins. So what will happen is that when calcium enters through the L-type voltage-gated calcium channel, it's going to come and stimulate these cells that are on the beta cell membrane, as well as those that are on the vesicular membrane. So when these proteins are activated by calcium, they are going to interact with one another. When these proteins they start interacting, they'll start pulling this vesicle toward the cell membrane. So they'll start pulling that vesicle toward the cell membrane. And what do you think will be the result? So the result is that this vesicle containing insulin and C-peptide sequences is going to fuse with the cell membrane. And when it fuses with the cell membrane, it's going to release insulin and C-peptide into circulation. So C-peptide is very important because C-peptide, it is released together with insulin. So this is used as a marker to assess the functioning of the pancreas. So for us to understand and know how the pancreas is working, or how much insulin we have in the body, we need to measure the amount of C-peptide in the body that we have. So this C-peptide has got a long half-life than insulin. So it's able to be detected in the blood. And what you should know that C-peptide is excreted by the kidneys. So you can also detect this in the urine. So this is used as a marker to assess the normal functioning, or rather the functioning of the pancreas. So you can use this to assess if there is low level or high level of insulin. Okay, that is very important. Now, I said that insulin release can also be triggered by other things. What are those things? We said that glucagon like peptide 1. Glucagon like peptide 1, this is an hormone that is produced by cells that we call L cells. So L cells, these are cells that are found in the distal ileum and the colon. So the L cells, they produce glucagon like peptide 1 hormone in response to glucose and fat acids in the GIT. So when there's glucose and fatty acids in the GIT, these things stimulates the L cells to produce what we call glucagon-like peptide 1 hormone. Now, glucagon-like peptide 1 hormone, it comes to the beta cells and it binds to what we call glucagon peptide 1 receptors or GLP-1 receptors. So these GLP-1 receptors, what you should know that they are linked to what? To a G protein, G stimulatory protein. So now, what you can see there, this is the G protein. So you find that when glucagon peptide 1 hormone binds to the receptor there, it's going to activate the G protein inside there. Now, when the G protein is activated inside, what is going to happen? Normally, the G protein has got 3 subunits, and these subunits are the alpha subunit, the beta subunit, and the gamma subunit. Those are the subunits of the G protein. So when glucagon like peptide 1 binds on the receptor, what's happening is that it's going to trigger the activation or the conformation change in this GS protein or in this G protein. So this G protein has got 3 subunits. So these 3 subunits, they are going to dissociate from one another. So what is happening is that the beta and the gamma subunit is going to be alone, while the alpha subunit, normally it binds to GDP, but when this hormone binds there, this alpha subunit is going to release GDP and it will bind to GTP. So it's going to become alpha GTP. Now, alpha GTP, you know what it do? Alpha GTP, it can go to another enzyme that we call adenylate cyclase. So alpha GTP can activate adenylate cyclase enzyme, and this enzyme, when it is activated, it is going to convert ATP to cyclic AMP. Cyclic AMP can activate protein kinase A. So protein kinase A, this is an enzyme that phosphorylates other molecules. So what will happen is that protein kinase A is going to phosphorylate or add phosphate groups to L-type voltage-gated calcium channel that we talked about earlier on. So you can see that protein kinase A is going to phosphorylate this channel right here. And when this channel is phosphorylated, it becomes open. As a result, calcium can flow in and it can lead to the translocation of the vesicles containing insulin. As a result, lead to insulin release. So we've seen that apart from glucose and ATP, glucagon and peptide 1 can also trigger the opening of these voltage-gated calcium channels. Now, I also said that there is another hormone that is produced by cells that we call the K cells. So the K cells, they are found where? These cells, they are found in the duodenum and jejunum. And these cells, they produce another hormone that is called glucose-dependent insulinotropic peptide. So glucose-dependent insulinotropic peptide, it is also known as gastric inhibitory polypeptide. This hormone is produced by the K cells. The K cells, they produce hormone in response to glucose and fat acids in the GIT, specifically in the duodenum and jejunum. So when these cells, the K cells, when they produce GIP, GIP will come here to the beta cells and it will bind on the GIP receptors. But what we should know is that the GIP receptors, they are similar to GLP-1 receptors. Why? Because these two receptors, they are linked to G stimulatory protein, or in short, they are linked to G protein. So they are G protein coupled receptors. So you can see that GIP is going to bind on that receptor, and then it's going to trigger a conformation change in the G protein right there. The G protein is going to dissociate, so its subunits are going to dissociate, the same thing that happened here. So you find that the alpha is going to bind to GTP, and it's going to release GDP. So it will bind to GTP and release GDP, while the beta and the gamma, they are going to form a dimer. This alpha GTP is very important. So alpha GTP, it's going to come and activate what? It's going to come and activate adenine cyclase enzyme, which will convert ATP to cyclic AMP. Cyclic AMP can activate protein kinase A. Protein kinase A, as we said earlier, is going to come and activate the L-type voltage-gated calcium channel, the one we talked about. So it's also going to come and phosphorylate the L-type voltage-gated calcium channel. The other thing that you should know is that protein kinase A can also activate phospholipase C. So it can activate phospholipase C, and phospholipase C, this is an enzyme that cleaves a molecule, a lipid molecule that we call phosphatidylinositol 4,5 base phosphate. So there is a molecule that is found in the cell membrane. So that molecule is a lipid molecule, by the way. It is called phosphatidylinositol 4,5 base phosphate. So protein kinase A can also activate phospholipase C enzyme. Phospholipase C enzyme, what does it do? Phospholipase C can further cleave a lipid molecule that is called PIP2, phosphatidylinositol 4,5 base phosphate. And when it cleaves PIP2, it forms two molecules. One molecule is called diacylglycerol, or DAG in short. The other molecule is called inositol triphosphate, IP3. Now, inositol triphosphate, what can it do? Inositol triphosphate, it can come and bind to the IP3 receptors that are found here. So there are IP3 receptors that are found on the endoplasmic reticulum. So when IP3 binds to the IP3 receptors, those receptors, they are linked to calcium channels. So what will happen that when IP3 binds those receptors that are found on the endoplasmic reticulum, which is a storage site for calcium in cells, it's going to release calcium. So upon binding of IP3 to the receptors on the endoplasmic reticulum, the endoplasmic reticulum can release calcium. And what calcium is going to do is that it's going to activate these proteins right there. And these proteins, they are going to cause the translocation or the movement of this vesicle containing insulin and Cpeptide. As a result, we are going to release that through exocytosis. So pKa can also use IP3, and IP3 is a second messenger. So IP3, like I said, can activate the endoplasmic reticulum to release calcium. Calcium will be used to move or translocate this vesicle and release insulin. That is another mechanism that can happen. So we've seen the triggers. So what are the triggers? So the triggers of what? So the triggers of insulin release, we have seen that glucose is the main one, but we also have two hormones, glucagon like peptide 1, GLP-1, and also have got what we call glucose-dependent insulinotropic peptide, or GIP. And also amino acids, they trigger the release of insulin. So when you look here, we've got this diagram. So in this diagram, we are showing a blood vessel. So we've got a blood vessel. So now, this blood vessel has got these cells. So these cells are called endothelial cells. So this is a capillary. It has got these cells that are called endothelial cells. So in the endothelial cells, we have got an enzyme that is called dipeptidyl peptidase 4. And this enzyme is also known as CD26. So this enzyme, it is also found in immune cells as well as epithelial cells. Now, what's the purpose of this enzyme and why are we talking about it? So this enzyme, what it do is that it breaks down glucagon like peptide 1. In other words, it reduces insulin release by breaking down glucagon like peptide 1. Now, why are we talking about all this that we've talked about? So the reason we're talking about all these things is that in type 2 diabetic patients, we have got drugs that can actually increase insulin release. And what you should understand is that when type 2 diabetes is starting, when it is just starting, there is high level of insulin in the blood. So at the beginning of type 2 diabetes disease, there is high level of insulin. There is hyperinsulinemia. But when it becomes chronic, after a long time, you find that the cells in the pancreas, the beta cells, they are going to become tired and they can't produce enough insulin. So you're going to find that this patient who had hyperinsulinemia at the beginning, later on in life, they develop hypoinsulinemia, low level of insulin. That's what happens. So these type 2 diabetic patients, when diabetes is chronic, they develop what we call hypoinsulinemia, which is low level of insulin. Now, how can you help them produce more insulin in the body that they need? So what you are going to do is that you are going to close it, which we are calling the ATP sensitive potassium channel. So when you close this channel, what will happen? You are going to find that action potential is going to be easily generated, which will allow the opening of the voltage-gated calcium channel and allow influx of calcium into the cell. So there are drugs that can inhibit this ATP-sensitive potassium channel. Instead of us depending only on ATP, we can give a drug. So there's a class of drugs that we call sulfonurias. So these sulfonurias, what do they do? So these sulfonurias, what they do is that they inhibit the ATP-sensitive potassium channel. And just a few examples of these drugs, we have got glipizide, we have got also glimepiride, tobutamide, and glibenclamide. So glibenclamide, glipizide, tobutamide, and glimepiride, those are sulfonurias. So sulfonurias drugs, what do they do? These drugs, what they do is that they inhibit the potassium, so they inhibit the ATP-sensitive potassium channel. As a result, we are going to easily generate action potential, which is going to activate these voltage-gated calcium channels and allow the influx of calcium into the cell. What other drugs do we have? We do have other drugs that can mimic the activity of glucagon like peptide 1 hormone. So what are these drugs? So these drugs have got exenatide, we also have got semaglutide, we have got dulaglutide, albiglutide. So those drugs, they mimic the activity of glucagon like peptide 1 hormone. As a result, when you mimic that hormone, you're going to find that you're going to increase insulin release. So remember, the patient that you're giving these drugs is a person who has got low level of insulin. So this is chronic type 2 diabetes. They've got low level of insulin. When they've got hyperinsulinemia, you want to increase the production of insulin. So you're going to give them sulfonurias, the one we talked about earlier on, and you can also give them drugs that mimic the activity of glucagon peptide 1 hormone. So when you give them those drugs that are going to trigger the release of insulin, more insulin, because they initially have got low level of insulin. And also we have other drugs as well that we call DPP4 inhibitors. So what are these drugs? So the DPP4 inhibitors, what they do is that they inhibit the peptidase 4 enzyme. So when they inhibit this enzyme can no longer break down glucagon like peptide 1. As a result, glucagon like peptide 1 will be able to stimulate the release of insulin by the beta cells. Because when you've got low level of insulin, we have to produce more insulin. So we don't have to break down glucagon like peptide 1. So what will happen is that these drugs, they inhibit the DPP4 enzyme. And what are these drugs? Got linagliptin, sitagliptin, and saxagliptin. So linagliptin, sitagliptin, and saxagliptin. These are the drugs that can inhibit this enzyme. So we are going to continue in the next video that I'm going to upload soon.